Thank you. Oh, a clap. Surprising. Okay, I'm gonna talk about personalized search and personalized recommendations, but I'm gonna start by telling you this is a hard problem. Okay, so when you want to create value with AI, you might first want to get your data house in order. So you probably have a data lake or a data warehouse. You'll do some BI on that data. And if you want to do AI or machine learning, you'd probably start on your laptop, do some laptop ML, fit some curves, some data, some curves. And then maybe you want to start building services. So I would call them a prediction service. So you might say, for example, I'm going to do a batch prediction service. So if anybody has Spotify here, you'll have something called Spotify Weekly. Once a week, you'll get predictions into your inbox. It's a batch program that runs over all 200 million users in Spotify. And it's nice, but it's not as good as TikTok. So if you're at TikTok at the top, you know, immediately as you're scrolling through your videos, it's learning about your behavior. It's actually not learning. What it's doing is updating the features or state on which the predictions are made. The models are static. But that's really operational ML with real-time data. You can also do operational ML with batch data. I have a surfing website that predicts the height of waves at a beach in Ireland. It runs once per day. It's an operational system, but it's using batch data. So we're going to talk today about personalized search and recommendations, and it's going to go all the way up to the top, the highest business value level. And we're going to do it for Python developers. So you'll only need Python to get through this. And you might think that this is a very difficult problem, and it is at some level. There's a lot of infrastructure you'll need. You'll need to have access to your enterprise data. We're going to need a feature store to store our features. We're going to use something called a vector database to store our embeddings and to look for similar items in the embedding store. And then we're also going to serve models. And traditionally, this would be a really hard project. You're going to put together data engineers, data scientists, ML engineers, but we're going to do it on Python. And just to annoy any data scientists here, we're even going to do it in notebooks. Right. Now, I wouldn't recommend you do that, but we're going to do it with notebooks. Okay, and we're going to do it on this platform called Hopsworks. It's open source. It's now available as a serverless platform as well. So what Hopsworks is, and best known as, it was the first open source feature store. So it's a Python-centric feature store. It also has model serving capabilities, and now it has a vector database. And what it will do is it'll connect to your data, your enterprise data, to this feature store and to the infrastructure for doing this personalized search and recommendations at scale. So we're going to look at a vector database based on OpenSearch, and then model serving on KServe, which are bundled with the platform. So let's start by talking about recommendation systems. So as you know, recommendations are typically used in domains like retail. I mentioned video streaming and music streaming. But typically, if you think about retail as a good domain, you have users who purchase items, and you can recommend based on similar items. So we call that item-to-item recommendations. So maybe people who tend to buy this item buy other items. Personalized recommendations, however, has to include attributes or features of the users themselves. So what's your shopping history been? What do you like? What's your preferences? What's your age? Where are you from? And this is what we call user-to-item recommendations. Now, if you're familiar with this space of recommendation systems, you might have heard of collaboration filtering as an approach. You may have heard of content-based filtering. And there's a few different domains here, but we're going to talk primarily about what's called the two-tower model for using embeddings to do personalized search. So I'm going to get into that in a minute. But a little bit of background. I mentioned Spotify Weekly is a batch recommendation system. Facebook and Netflix have had very famous batch recommendation systems. If you work in data science, you might have heard of the Movie Lens dataset. It's often used to do recommendations, but primarily it's for batch, so offline recommendations that you will write to a database, and you'll consume those later. So at the high end, what we're going to talk about today is more about real-time recommendations. So systems that will make recommendations using what's called a retrieval and ranking architecture, and TikTok, as I mentioned already, are a canonical example of this. The retrieval and ranking architecture came from YouTube originally, but we'll go into that in a minute. So just to put it in context, what is a batch recommendation service? This is a pretty standard or typical architecture for doing batch recommendations. You have your raw data coming into a feature store, and then you'll have a program that might run daily or hourly. It'll read the batch data to be scored. It will compute the predictions using a model that downloads from model registry. It'll store the predictions in a sink somewhere, so maybe in a key value store database, and then it'll consume the predictions. So if it's Spotify, it'll push it into Cassandra, and then when you log on in Spotify, it'll just download those predictions, and then you'll see the weekly songs that are available. But this is also used for reports, so predictive analytics and reporting is often done in this way. Now, real-time recommendations are a bit different. This is a very abstract model of what a real-time recommendation system does. On the left-hand side, we have a database of items, so you can have millions or billions of items. I'm going to use the example of H&M. There's a Kaggle data set about H&M items. It's clothing. So we have millions of items there. And when I want to recommend items, for example, pieces of clothing at H&M, I need to first generate candidates. And then so I'm going from millions of items down to hundreds of items. And then those candidates I want to rank. So when we're doing personalized search and recommendations, we need to use the user's history, but also context. So what's trending right now, what's popular. And then what we'll get out are ranked candidates that the user may or may not click on. So the infrastructure you need for this, to build this retrieval and ranking architecture, there's really three parts, and I've kind of introduced them already. So the first one is when we want to go from billions of items down to hundreds, we use the vector database. We're going to compute embeddings from the user's features, but also from the items features. And the thing you've searched for, or maybe the last item you clicked on, we'll take features from those as well. And we'll use that embedding to look up the best candidate items, because we're going to recommend items to the user. To do that, to compute the embeddings, we're going to have to need to get history and context from the feature store. And then we're going to have to make the models available somewhere. So we can serve them, in our case, we'll serve them in KServe. And you can see there's a little bit more infrastructure around that you'll need. You'll need pipelines to feed the feature store with features and keep them updated. They could be batch or it could be streaming pipelines. And you'll need a model registry to manage your models. So just a little bit, if you don't know what embeddings are, an embedding it's a mapping of a discrete or categorical variable to a dense representation. It's effectively an array of floats. So it's a dense representation of this sparse space. And what you can do with embeddings is you can do what's called similarity search. So if we look at the diagram on the left, we have what are called hops. We're Hopsworks. And you can see similar hops, images of hops. So what you can do is you can take the image, you can compute an embedding over it, so you convert it into this array of floats, and then you can say, show me the most similar images. And you can do the same with words. You can take all of the words in the English language and compute an embedding from them and insert them into this index. And then when you have words like fast and faster, you can even do arithmetic on them. You can say fast plus faster, what does it equal to? And in the embedding space, the closest answer will be fastest. So embeddings are quite magical things, but they're very powerful. So with our embeddings, we're going to create embeddings over the items, also over the users. And in fact, we're going to do something even crazier. What we're going to do is we're going to map from the user space into the item space. And that's what the two-tower model will do. So the way we're going to do that is we're going to jointly train the user embeddings and querying embeddings. It's something called a two-tower model. With that, we can build this index of items. And when I want to search for something or the last item I clicked on, we're going to use this nearest neighbor index to find the most similar items. So maybe you've searched for a piece of clothing, or you've clicked on some piece of clothing, or bought something in the recent past. What we're going to do is we're going to find the best item that's closest to that embedding that contains both your personal user features and then maybe the last item you clicked on or the items you bought recently. So that's what we call the retrieval phase. So we have our embeddings first, and then we're able to retrieve the candidates. We often do filtering after that. So filtering could be something like, hey, if I'm recommending movies, don't show underage users certain movies that are R-rated. That's a static feature. You can do that in your similarity search. So in OpenSearch, you can filter as well, but it's typically only static features that you're going to include there. A lot of the other features you might have, such as I don't want to show the user items they bought recently, that will go to the feature store, because that's a dynamic feature that you'll need to look up and will be updated potentially very frequently. And then the final step, when we have a number of candidates that we've got back from the ANN index, we're going to rank them. And we're going to do that with machine learning again. We're going to use something called a ranking model. It needs to be very fast. But when we get the candidates back, we're only going to get the IDs of these items back. So we need to enrich that with features for the items, but also features for the user. And then we want to ensure things like that the items returned are diverse and so on. So the feature store, what it does here in this architecture, the retrieval and ranking architecture, is that the user wants to click on or search for something or click on something. The feature store is going to give us are basically pre-computed features. So it's going to give us information about your history, your context, because this application on the right-hand side, it doesn't store information about what you've clicked on recently, what you've bought recently. It's a stateless application. It's a web-facing application. Maybe it's in Node.js. But the feature store will store all this data about you and what's popular and trending in the system. And then we can use those pre-computed features to enrich our feature vectors that we make the predictions with and that we do similarity search with. So in this case, if I give the example of the H&M data set, we actually had 3 different pieces of information. There's 3 different data sets on the Kaggle data set. One is the users who are buying items in H&M, the items of clothing that are available. And then the transactions are the items that are bought by users. And that's the link between the user features and then the item features. So these may come from different systems. They may come from a data warehouse, Kafka for your transactions. And we write them into feature groups. So feature groups are just tables of features in our platform. And we want to read from the feature store to create training data, so with this offline API. What we do is we basically select features. We say, I want that feature from the users, this one from items, these ones from transactions, and I want a feature view for that. That's going to be my ranking view, for example, or it could be my retrieval view or user item pairs or whatever. So you can define these. These are logical views over the features, and you can then retrieve training data from them with the offline API. But when you're serving these models, you can go to the online API to get back feature vectors with the pre-computed features at very low latency. So how do you write to the feature store? Well, you can write in Python, Pandas, which I'll demo, or you can use Spark or Flink. If you have tables in an existing data warehouse like Snowflake or Databricks, you can just mount those in as tables into the platform. Now, the other thing that you need to do is, well, how do we get this data? I didn't tell you how we got this data. How do we get the information about users buying products? Well, obviously, you're going to have some system set up where by when a user purchases a product, or maybe in this case, we can see a website where we've presented a number of items or candidates to the user, and the user has clicked on one. Maybe they bought another one. What we need to do is log this information, because we're going to use this information to train our ranking model, but also to help compute the embeddings. So you can see here that if a user clicks on something, we'll give it a score. If they buy it, we'll give it a higher score. And we use that information then to create training data with. So if we look at this from an infrastructure perspective, we have our user items, the users and items coming from the data warehouse. We have maybe historical transactions coming live from Kafka. Maybe we backfill from a data warehouse or data lake. We compute features from them, and we write them to the feature store. And then what we have on the right-hand side is we're able to retrieve the features as training data to train different models. Here we have 3 models. We have the user and item embedding models, and we have then the ranking model. But the other thing that we need to do is we need to write all of the items to our approximate nearest neighbor index in OpenSearch. So what we do is we just have a Spark app that reads that data, or a Python app computes embeddings on them and writes them to the index in OpenSearch. So the kind of magical thing, or thing that's a little bit different, and you won't find too many examples on this on the internet. So Stack Overflow isn't full of examples of 2-tower network architectures. There's a TensorFlow library called TensorFlow Recommenders, and it has a good example you can build with. We have an example that's I'll show you later on. But basically, what you're doing when you're training your item embedding and your user query embedding is that you're basically feeding the item features into the item tower. You're feeding the user features into the user tower, and the loss function you're computing is you're saying, okay, this user bought this particular item. Let's see if that item, if the point in embedding space that the user query pointed to and the item query pointed to, if it's close to the item that you actually bought. And if it's far away, well, then we have a high loss. And if it's close together, we have a low loss. So we're going to use that loss then to train both of these different towers. So there's different loss functions you can use. Cosine Loss is one form, but there's a bunch of other ones. So dot product or sigmoid are common. So the ranking model is the model we're going to use later on to rank the candidates. And what a ranking model basically does is we have the features log. The ground truth at the bottom are the logging when users clicked on things and didn't click on other things and maybe bought things. So that's what we're going to use as the labels. And then we're going to get a bunch of instances where users clicked on things or didn't click on things. And we're going to train the model, basically, based on that. Now, you do need you have these positive examples where users clicked on things, but you need a lot of negative examples as well where users didn't click on things. Otherwise, it's hard to train these models. Typically, they're gradient boosted decision trees because they need to be very fast. So the feature store can give you the training data. You can train your models. In the example, I have embeddings trained in TensorFlow, and then CapBoost to train the ranking model. And then we store the models in a model registry. Now, in our case, we have a model registry in Hopsworks that's designed specifically for KServe. KServe is pretty much the de facto model serving framework for Kubernetes. But once we've trained our models, then we can include them in our architecture. So now we can see that as well as the feature store and our kind of retrieval and ranking system in the middle, we have the models being queried in KServe, and then we have OpenSearch used to query or do our similarity search. So when a user clicks on an item or types a search query into the browser, the retrieval and ranking system will firstly compute the embeddings. It'll go to OpenSearch to find similar candidates, and then it'll use the ranking model then to rank those and return the ranked results to the client. So what that looks like in terms of flow in our system is the following. We have a user query, and the user basically, when we say user query, it could mean that you type text into a box. It could be, I've just purchased a product, what's the next product I'm going to purchase? Or maybe I have, in this particular session, a history of items I've looked at, and then I've got to predict the next item that I want to look at. So there's different types of recommendations you can do. If you're doing a shopping cart recommendation, it might be different to a landing page recommendation. But basically, the user has some sort of query. We have information about the user identity, what they've done recently related to items, and we're going to go from that user identity to the feature store and retrieve the features related to that user. So the pre-computed features, maybe it's your information about what you like, what you don't like, your age, where you're from, and then we'll retrieve features related to the items potentially as well, because we can feed the recent history of things we've browsed, because they can also be part of the user query embedding. So to compute the embedding, we take all of this information and we run it through our embedding model. Now in this case, you can have the embedding model hosted in your service, so it could be embedded in your service. It'll be a little bit quicker, because in this case, we're going over the network. We're making network query to KServe saying, here are the features, please return to me the array of floats, which is our embedding. So when we've got our embedding, what we can do is we go to OpenSearch and say, hey, I want 250 candidates, and this is similarity search. We'll get back our 250 candidates, and those 250 candidates will be just items. They'll be the item ID. Maybe we'll have some other small pieces of static information. Maybe we care about filtering out underage items that are not suitable for underage people, so we include the items rating, and then we can say, okay, filter out these that are not suitable for that user. In the example we have, we also filter out with the H&M clothing, we filter out items that you've already bought. Now, you may say that's not a good idea, maybe people want to buy again, but there's a lot of creativeness that you need to go into building these systems. So you've gotten back your 250 candidates, so you have the item IDs. We know the user ID as well, but we want to rank them. So to rank them, we need more than just the user ID and the item ID. We need the features related to the items and the user. So again, we need to go back to the feature store. This time it's a very challenging problem from a latency perspective, because I may have 250 different IDs for articles and I need to look up 250 feature vectors for those. So that's going to be a batch lookup on the feature store. It needs to be low latency. That's why you'll see a lot of feature stores are built around in-memory databases, including ours. And then finally, once you've gotten back all the features, you need to rank all of the candidates that you have the features for. So we're going to do a batch lookup on our model, our ranking model. We send the batch of 250 feature vectors, and they'll get back a score, and we're going to sort them based on the score and return the rank results to the user. Now, you're not done yet. This is pretty much the whole flow of control, because the user is going to click on something, aren't they? They're going to say, well, I clicked on that, or maybe not going to click on anything. And we need to capture that feedback, because that feedback is worth its gold, right? That feedback enables you to create new training data to make better models. And with more training data and better models, you'll improve your recommender system. So we need to log the outcome, so what users have clicked on, what they haven't clicked on as well, negative samples, back into the feature store. So just to give you an idea of the kind of challenges of this at scale, we work with Spotify to, they're looking at a ranking retrieval infrastructure for personalized search for songs, but they need to do it at incredible scale. So they looked at in-memory databases that would be suitable for this particular challenge, and our database, RonDB, is one of the highest performance ones out there. And they actually didn't include databases like Redis or Cassandra or Bigtable. They did a comparison of Aerospike and RonDB. So this is the experiment setup. It's just a bunch of virtual machines on Google Cloud. But RonDB, with just 6 nodes, was able to handle, I think, 2 million operations per second in throughput. With 8 nodes, I think it grew a little bit. And then the latency was very interesting. For 250 lookups in the feature store to get back the features, the P99 latency is still under 40 milliseconds. So that's pretty impressive. Or 30 milliseconds, sorry. For RonDB, it's 30. For Aerospike, it was 40. So this is pretty interesting tech. There's a link to the report if you're interested to read it. And what I'm going to show you is that, that's kind of at the high end. That's the scale, the challenges you have at scale and the really big ones. But you're a Python developer. How can I do this? Like, this all seems so crazy and huge, really interesting, but I wouldn't know where to start. So this code is available. It's currently in a branch there, but we'll merge that to main soon. But we basically have a set of notebooks. You can see there's like in total 7 notebooks, and they're doing 7 different steps. And I'm going to go through the notebooks just to show you the code. So the first one is where we do feature engineering. So feature engineering means taking your data, your raw data, computing features on it, and writing it to the feature store. And that means just writing it to feature tables. We're going to do it in pandas. In this case, we often might have 2 code paths. One is what we call backfilling with historical data, and another one might be taking all the live data that comes in. So there probably will be in a production system an orchestration component to this. You want to orchestrate it with something like Airflow or some other orchestrator. So it's going to continually write and update your data. But let's have a look at the code. So the second notebook is going to be just creating a feature view from the tables that we created, or the feature groups. So let's have a quick look at it. All right, so here's notebook number 1. So we have, this is from Kaggle, this data set. There's an articles CSV file, customers CSV file, and then the transactions. These are the user has bought this item. So it's really simple. You just read up your CSV files into pandas data frames. And then we do some feature engineering, some very simple feature engineering. And then you write them to feature groups. So what's interesting about a feature group, if we can see this, maybe I'll zoom in a little bit. We can see that the feature group is this is our data frame that we created, and we did some feature engineering on it, customers DF. But the feature group just needs a name, a version, because versions are important, because that's the version of the schema of your data frame. If you drop columns, or if you change the implementation of an embedding, that training data will never be compatible with the old one. So you need to increment the version. But for MLOps, this is really important, because you can have a production pipeline running on version 5, and then users can create new training data on version 6, train their models, evaluate them, and then when you're happy, you can switch over from version 5 to version 6 in production. But the only thing that you need to do here is we're going to retrieve this data with the online API, so with low latency. So I need to say that that's enabled, and then you need to give it a primary key. The same is true for the articles. The articles have a primary key, which is the article ID. And then for the transactions, we can see that we have both a customer ID and then an article ID. So a customer bought this ID. And we also have something called an event column. So this is the time at which the user bought this piece of clothing. And we're going to use that for point-in-time correct joins, which I won't talk about too much here. So let's have a quick look. we're at number 2. Okay, so the next thing I need to do is create the feature view. So I get references to my feature groups. You can see they're versioned as well. And the way we create the feature view is we have this domain-specific language, right? So it's a very simple way of joining together features from different feature groups. Now, this is actually a really challenging problem because, you know, a user bought an item at this point in time, but we need to have the correct features for the user at that point in time. We need the correct features for the item at that point in time. So if you were to do this in SQL, in the SQL world, you would write a very complex SQL query, and what it would say is, here's the transaction, here's the time at which the user bought the item, select the features of the user where the timestamp for that feature is less than this feature where you bought the item, but the most recent one. And that's not something databases do, it's not something Spark even does. We had a blog post today that we posted about writing our own Spark operator. We wrote our own Spark operator to do this efficiently. But we don't present that to the users. You don't need to write that really complex SQL. All you basically do in a pandas-like syntax is you say, select these features from the transactions feature group, select these features from the customers feature group, and these features from the articles feature groups, and join them together. And then we can specify the join key. It can also, the query optimizer can discover the join key if it's common between the two as a primary key. But here we're making it explicit. So this object we get back, you can inspect it, you can get a data frame from it, have a look at it. You can also just say, make this register with the feature store as a feature view. And so it's not going to make a copy of the data, it's just going to register the schema. And then with this feature view, you can go and create training data. So training data in this case is going to be a CSV file, could be TF records or something like that. You can get training data as pandas data frames as well, but in this case, we're just writing it to a file. So that's the first part. So the second part is we want to now train our retrieval model. So we're going to train the two-tower model, and then we're going to populate the index in OpenSearch with our embeddings. So the first part, we'll have a look at it, is here. Let's have a quick look. So this is the two-tower model that I mentioned earlier, and what we want to do here is we're getting our training data from the training data set. So this is the training data set we just created. It's already split into training and validation sets. So what we want to do is basically, firstly, we need to get the list of the different categories. We want to convert our data into we're training with TensorFlow, so we're going to convert into a data set in TensorFlow. And then we create our user tower. So it's a Keras model, so we're implementing the Keras interface, and then we have our embedding. It's just a very simple TensorFlow embedding. And we put in the user's age as another feature in here. So this is for users. You can, of course, add more and more features in here as you need them. And when it's actually being called, it's going to create the embedding this way. And the same is true for the user tower. So the item tower. In the item tower, we don't have that many features. We have the group that the item belongs to in terms of the close. And also it belongs to a different index. So we add those as features. And now we have the two towers. So with our two towers, what we do is we're using, in this case, the TensorFlow recommenders framework to put the two towers inside this two-tower architecture, and then the training is done jointly over both of these two towers. And it's pretty straightforward. I'd refer you to the TensorFlow recommenders tutorial to learn more. So we've trained a model. All we need to do then is upload that model to the model registry. We're adding a signature to it here because we just want the customer ID. We want to add that as well. So IDs typically don't belong as features, but in this case, we're adding it. And then we save the schema of the model, and we just basically save it to the feature store. So what will look like at this point, I'll just go back and show you visually. At this point, we now have feature groups in the platform. So we've got customers and articles, and we have feature views as well, right? So we have the retrieval feature view. You can see I've already run this, and we have a bunch of them. Now, the platform's pretty good for doing things like exploratory data analysis. So EDA, you can see what features are there, provenance, what feature groups are used in what training data sets. If you have great expectations or tagging, that's all there, alerts. You can get a preview of your data pretty quickly, both from the online and offline stores, and you can look at the activity in the feature group when people read and wrote to it and so on. And you can see more metrics. Now, in the model that we wrote, the model got written here to the model registry. You can see we've got 3 models here at this point in time. Okay, so the next thing I need to do is write all of the items to our index, the OpenSearch index. So let's have a quick look at that. Again, this is all Python code. So what we want to do here is we want to basically read up all of the items. So you can see here we're basically getting all our items and we're computing embeddings over them. So this is the line that's computing the embeddings over all of our items. So now we've got all of our embeddings in this particular data structure here. And we just need to write it to OpenSearch. So in our platform, we have support for OpenSearch. We have an index. This is the KNN, K-nearest neighbors index in OpenSearch. It's using FICE as the index underneath it. And unfortunately, they don't have a really great Python API yet, so you have to write this REST-like or JSON dict to describe your index. This is our index here. It's using, the embedding dimension is I think 16, and we're using the FICE engine, which is one of these ANN engines. So basically, when we want to insert data, we do have to put in this dict. So we're just appending the embedding, which is this one called myVector1. The item ID we'll be able to get back when we get the similarity versions. And then we just do a bulk insert. And then you can also do queries as a check if it's OK. So that code is not too complex. And you can insert tens of millions or hundreds of millions of items in here, and it's pretty quick. So what have we done so far? So the next thing we're going to do is we've built our ANN index. We have our feature groups and feature views, but we haven't trained our ranking model yet. So we need another feature view for the ranking model, and then we need to train the ranking model. So let's have a quick look at how we did that. So it's very similar again. So we have number. Okay, sorry, I'll zoom out of it. So this is where we create the training data. Again, we get reference to our feature groups. In this case, we're creating a feature view for articles because we need to look those up in customers. But this is the, so then we're basically doing a little bit of feature engineering because what we want to do for the ranking models, we need both positive examples and negative examples. So that's happening here. I'm basically taking the items that users have clicked on, the transactions of things that they bought, and we're just replacing the ID with a random ID and assuming the user didn't buy that ID, that particular item. But here we've got a ratio of 10 negative examples to 1 positive. And that's something you have to play with a lot. So when we basically label the positive pairs as having 1 and 0 for the negative ones. That's where users didn't click on an item. And then we create a feature group and a feature view for their ranking data, and then we create training data. So once we have training data, what we can do is we can train the model. And I said before, this is cat boost. So in this case, we're retrieving our training data as pandas data frame. We just get our feature view and say, I want to train test split. And we get back pandas data frames for the different training features, test features, and then the training labels and the test labels. And then we use cat boost to train the model. And again, we're going to do the same as before. We can store the metrics of the model in the registry along with the actual model itself. So here we're just uploading the model to the registry, and now it's available. So if we go back and look at the platform here, we now have our ranking model here. And if we look at the ranking model, we can see the metrics. This is version. You can have many versions. This is version 1. But if we look at version 1, we can see the metrics that were computed, the schema of the model, and any tags and code snippets for how to use it. Okay. So then finally, we want to actually deploy the model. And we're going to deploy it in KServe. So this one is a little bit more complex. I'll just show you the diagram here. So I mentioned that we have a ranking retrieval service, but in fact, you don't need to implement a whole service. You don't need a microservice. What you can do is you can just deploy your models in KServe. And every model that you have in KServe has 2 parts. It has a transformer, which is a Docker container, a Python program that runs before the actual model, the predictor part. So at the top, we can see we have the user query model, which is in this predictor. And then we have a piece of code, a transformer function that runs before it. And then for the ranking model, we have a transformer again, and that calls in a predictor. So we can actually implement all the logic we saw earlier for retrieval and ranking with that code. So it looks like this. This is our predictor component where we make the predictions. Then we have the transformer. It's connecting to the feature store, and it's retrieving features and going to the OpenSearch index. And these are both of our, you can look up this code on GitHub because there's a little bit more details in it. But basically, you get a model that runs here. We can see the models running. And we can see we've got a couple of models running in there. So all you need to do then is put a front end on it, and you're good to go. And that can be like a Streamlit application. So I think I'm out of time. So I'll jump back. And this is our model being used here. If we get some, this is the model being deployed and run there. And you can get your logs and metrics for it. OK, so to finish up, where do you go next from here? Right? Imagine you've done this, and you're really happy and think this is great. Well, what you would like to do is you'd like to capture all the logs we talked about, the prediction logs, the feature logs. What's very important here is you capture the untransformed feature logs. So if you're storing transformed data in your feature store, not so good. You need to basically get the untransformed logs, push them into your feature store, and then you're able to use that to train better models, create more training data, which enables you to get better models, and you keep making the system progressively better. Now, if you want to try this out, this is available in Hopsworks as a serverless feature store. Go to app.hopsworks.ai. It's free forever. It's like Dropbox, Trello. This is where we want you to store your features, your models. We want you to basically use this to build prediction services, not just models. Okay, and if you're a data scientist and you're doing a sprint and you go to your boss and show them a model that you've fitted some data, it would be much better to show them a prediction service that does something. It takes data, it keeps updating the data, and it has a user component to it, maybe a user interface, that they can use to basically show the value that your model adds. So this is something you can try out. It's brand new. We're announcing it here for the first time. But please go and try it. So we're Hopsworks, and I think I'm over time. Thank you very much.
Thanks, Jim.